All right, we are going to be starting chapter 24, and that is about magnetism. So we are going to be looking at part 1, magnetic forces and magnetic poles, and magnetic fields and magnetic domains. So this is about how a magnet works, okay? So why are some things magnetic? So magnetism is closely associated with electricity. And so when we're looking at magnetism, this is a result of some electric process that's taking place. Electromagnetic waves, which remember we talked about those, radio waves, infrared waves, and so on, those are electromagnetic waves. And those are actually made up of electric fields and magnetic fields. Now, of course, a magnet, we usually consider it to have two poles. But what do we mean by a pole? Is there something actually there? When we think about a charged object, well, there's actually charges on something. But what do we have when we have a magnet? And of course, those poles are called north and south. But a magnet doesn't have to have only two poles, but it does have to have at least two poles. So the magnetic force that is experienced is due to the motion of charged particles, usually electrons, and the electrons orbiting the nucleus of an atom create a lot of the magnetic dipole moment, it's called. But also the electrons themselves spin. Anyway, electrical and magnetic forces are both part of electromagnetism. Now, originally the north end of a magnet was named north because it points to the north geographic pole. And the south end was the end that pointed towards the south geographic pole. And we'll talk about later, this has some interesting implications because norths are attracted to souths. So what kind of pole is the north geographic pole? What kind of magnetic pole might it be? So we'll be looking at that later when we talk about the Earth's magnetic field. Magnets can repel each other, of course. The north and the south will repel. And of course, that's much like when we talk about electricity, how positives and negatives are attracted, but positives are repelled by positives and negatives by negatives. Same sort of thing with magnets, right? Norths attract souths, but souths and souths are repel each other, and norths repel each other. So when we play with magnets, then we see that they will have at least two poles that are repelling and attracting. So let's take the camera over here, and we have a magnet hung up. Okay, so we've got a magnet with a north end in red and a south end in silver. And we're going to bring another magnet up and see how these silver ends repel each other. But it will attract, of course, the red north. The south attracts north, switch to the red, repels the red. Right. And I can get it to circle too. Well, getting it does help, but I can also get it to circle just by repelling it at the right time. And this is actually one of the ways that sort of an electric motor works. Is you have repelling and attracting at just the right time to keep something moving around. Sorry about that. All right, there you are. Okay, we'll be looking at some other fun magnets too. This is a natural magnetic material called magnetite. And so it's a rock that has a lot of iron in it. And it's naturally magnetic, so it's got the magnet stuck to it, but also just a paper clip will stick to it too. Okay, so it's not strongly magnetized, but could it get more magnetized? Let's go look at how some materials, why are some materials very magnetic and others are not? Uh-oh. Lost my camera. Oh, got turned off somehow. There, should come back. There it is. All right. Yep, got the wrong one. Switch camera. There we go. All right. So, anyway, so when we're looking at magnets, the north and the south isn't always obvious. It's not always sticking at the ends with a label that says north and south. So when we have like the flat magnets on the right side, those refrigerator type magnets, also, they cling to a surface, or in this case, repel each other, because the flat surface is either like all north, and then the other surface here, that would be a north, and then their other side would be a south, and that would repel a south, and then we would have another north side. So the actual side is a north and south. And like I said, magnets can actually have more than one magnetic pole. So refrigerator magnets often have areas of magnetism like this, where they would have north, south, north, south. So anyway, so weirdly enough, they don't just have two magnetically polarized areas. So let's go learn about why you can do that. How can you have more than one pole? And again, what is at the pole? Now we'll be talking about magnetic fields also, okay? So between the ends of the magnet, it's a magnetic field. Okay, so what's a magnetic field? It's a set of imaginary lines that indicate the direction, as if a small compass needle was placed in that location. Okay, and so the compass needle is being pushed around by the magnetic field. So it lines up with it. So there's a force on the compass needle, and that applies a torque, right? A force times a lever arm. And so it tends to create alignment between the needle and the magnetic field. And just like when we talked about electric fields, magnetic fields are vectors. So here we have some little iron filings, which basically is you take a bar of iron and you rub it on a file. And so the idea is that these iron pieces can be made into magnets. So when you pick up a paper clip, an iron paper clip, it too becomes a little tiny magnet, and it'll create with an end, one end that is north, one end that is south, not because it comes that way, but because what happens is when it gets in the magnetic field, it will line up with it. It'll line up the domains, which we're going to talk about. So anyway, so each little piece here becomes a mini magnet temporarily, not permanently. And so they line up. And they will line up such that they follow the magnetic field lines. Okay, so put in lots of compasses and you would see the compasses lining up on those magnetic field lines. And field line arrows, they point out of the north end of the magnet, and into the south end. But notice that they continue right through the magnet. And in fact, there's nothing special, it looks like, about the north and the south locations, right? The magnetic field lines exist, but they don't radiate from those points. They're kind of just points that we put a label on to be convenient. They're kind of where the lines appear to be coming from, but we've got lines over here too, and here, and here. So they're not really radiating out from that point exactly. Okay, and that's because, yes, the magnetic field lines run through the magnet. Okay, now, why are some materials magnetic and some are not? Most materials are not magnetic. And usually that's because a lot of the magnetism comes from the spinning electrons. And usually you have pairs of electrons and they spin in opposite directions. So their fields cancel out each other. And so we've got lots of electrons and they cancel out. And so usually those make non-magnetic materials. But there are just a few materials that are ferromagnetic. The best of those is iron, but then there's nickel and there's cobalt too. And so ferro, of course, is the word for iron, which is why it has the symbol Fe. So ferromagnetic, magnetic like iron. And iron has, I believe it's 4 electrons that do not cancel each other out, and nickel has 3, and cobalt has 2. And most materials at most have 1 electron. So they are not ferromagnetic. But iron has a whole bunch, 4, that do not cancel each other. Now, so each atom has a little magnetic field, and the atoms will line up with each other in what's called a magnetic domain, which is a region of magnetic alignment where those atoms all have their little magnetic poles all lined up the same direction. But then there's another domain that might be nearby where they line up in a different direction. So you can still have lots of domains, but the material might still not be magnetic to the outside world. So let's look more at this. If they're randomly oriented, like this, so these are representing domains, then it's non-magnetic. But if you can get those to line up, then you've got a material that's magnetic. And one way to do that is to actually place it in a coil of wire with a current running through it. And that creates what we're going to call, later we'll talk about, the electromagnet. And that will create a strong magnetic field that the iron can line up on. Now, you can also take iron and just hold a rod above your head and point it north and south, and or it doesn't have to be above your head, I guess. Tap on it gently with a hammer, ding, ding, ding. Every time you're tapping on it, what happens is that the little domains start to line up with the magnetic field of the Earth. And so this can happen in factories where the machines are vibrating and they start to get magnetized. And I was in a restaurant once where evidently their dishwasher lined things up beautifully because all the forks and knives and spoons were magnetic. Okay, so yes, you can take a regular piece of iron, get these domains to line up, and it will become a magnet. Okay, so this again, these are showing the domains are represented by these arrows. And you can see how they, as you line them further and further up, the magnetic field gets larger and larger. And you can also see, though, that there's nothing special about the point that's represented by a south and a north. Those are not special places. The magnetism of the material is due to those domains being lined up, and those are throughout the material. And this also explains why, when you break a magnet in half, why you still have 2 magnets, because the domains are still lined up. And so you've just created two magnets that don't have as much strength as the original one, but still two magnets for the price of one. Okay. So anyway, so it's the domains lining up that create the magnetism. And the domains are where we have atoms that have an excess magnetic field. Okay, now here we've got a fellow with some nails hanging off a magnet. And let's say that this is the north end of the magnet. What is this down here, the very point of the very last nail? Is that a south or a north? Well, since the north is up here, every nail that's attached, it will create a south end that is attached to the north, and then the other is a north. And then the next nail that's attached will also have a south pointing to the north, and a north, and then the next one, south, north. And so finally your last nail is still going to be doing that, south at the top, north at the bottom. Okay, so yeah, so you're creating many magnets, but they still have to obey the rule that like magnetic poles repel and unlike ones attract. Okay, and that is the end of part 1.